Hydrogen production from coal. The talk today will cover hydrogen as a fuel, look at hydrogen markets, the techniques for producing hydrogen, and how these compare in terms of costs and emissions, hydrogen strategies that are being rolled out and the supporting policies, and finally wraps up with some conclusions. Hydrogen as a fuel. Hydrogen is gaseous at atmospheric pressure and temperature and is most commonly found in the form of water, but also in hydrocarbons such as coal. It is non-corrosive, although it can cause embrittlement of some metals and alloys, which has potential implications for materials choice in pipelines and system components. Gaseous hydrogen is around 14 times lighter than air. This means that if released in an open environment, it will typically rise and disperse rapidly, representing a safety advantage. If released in a confined space, however, any hydrogen leakage can accumulate and reach a flammable concentration. Adequate ventilation is therefore required, with the use of detection sensors recommended, which is further exacerbated by odorants not being fully consistent with hydrogen because they are not light enough to disperse with hydrogen at the same rate. Hydrogen has a high energy content of 120 megajoules per kilogram on a mass basis, whereas on a volumetric basis, the energy content at 10.8 megajoules per cubic meter is relatively low. This is a particular challenge for storage, where to store sufficient quantities of hydrogen gas, it is typically compressed and stored at high pressures. Hydrogen can be classified as grey hydrogen, where the hydrogen is produced typically by steam methane reforming of natural gas or by gasification of coal. Blue hydrogen, produced from fossil fuels as per grey hydrogen, but now including carbon abatement, and green hydrogen, produced through the electrolysis of water using electricity generated from renewable sources. There is a growing interest in the potential of hydrogen to become a clean energy carrier. The primary reason for this is its ability to support the reduction of greenhouse gas emissions. Hydrogen is an energy carrier rather than an energy source, which means that its potential role has some similarities with electricity. A key difference, however, is that hydrogen is a chemical energy carrier, which means that it can be transported and stored in ways similar to more conventional fuels. It can be used in largely existing transportation and utilization infrastructure, allowing the adoption of business models developed previously for conventional fossil fuels. Hydrogen is supplied almost entirely from fossil fuels, with coal accounting for around 27% of the hydrogen demand, natural gas accounting for over 70% of the hydrogen demand, and electricity as an energy input for electrolysis accounting for less than 1% of the hydrogen demand. In energy terms, the total annual pure hydrogen demand worldwide is around 330 megatons of oil equivalent, equating to 70 to 73 million tons of hydrogen per year. The hydrogen is produced in dedicated facilities, primarily local to the point of use, and its main uses are upgrading of petroleum products in refinery applications and as a feedstock for ammonia production. In addition to this dedicated hydrogen demand, there is a further 45 to 48 megatons of hydrogen per year produced as a byproduct from other processes used for the manufacture of methanol, in the manufacture of steel, and as a synthesis gas for fuel or feedstock and process heating. A number of assessments of the future demand for hydrogen are being carried out. In all of these, hydrogen is seen as a necessary feature of the energy transformation required to limit global warming, where it could play an important role as part of a broader strategy. The breakdown of the forecast use of the hydrogen demand in 2050 is shown here, with a total demand of up to 78 exajoules or 650 megatons per hydrogen. This hydrogen will be used primarily for industrial feedstock and energy, together with transportation, heating and powering buildings, and power generation usage, including hydrogen buffering. The spread of hydrogen usage across these sectors is reasonably uniform, with significant quantities of hydrogen used in each. Turning now to hydrogen production. Hydrogen production from coal using gasification is a well-established technology used for many decades by the chemical and fertilizer industries for the production of ammonia, particularly in China. In the gasification process, a hydrocarbon-rich feedstock, such as coal, is heated at high temperatures to produce a syngas rich in hydrogen, carbon monoxide and carbon dioxide. The syngas can then be upgraded by converting the carbon monoxide to carbon dioxide and more hydrogen using the water-gas shift reaction. The CO2 can then be separated using relatively mature physical absorption technologies such as Selexol or Rectisol, which means that coal gasification can be a low-carbon hydrogen production technology. The process can produce a stream of hydrogen of around 99.8% purity using a final pressure swing absorption step. In terms of gasification with carbon capture, there are currently 3 facilities producing hydrogen from coal, coke and petcoke at scale, with a combined capacity of around 0.6 megatons of hydrogen per year, namely Great Plains and Coffeyville in the USA and Sinopec Kuala in China. The Great Plains plant alone produces 1,300 tons per day of syngas, demonstrating the large-scale production of low-emissions hydrogen using carbon capture can already be technically and commercially feasible. Additionally important to the Latrobe Valley gasification pilot plant in Australia, as part of the Energy Supply Chain project that will see hydrogen produced in Australia shipped to the Kobe plant in Japan for utilisation. Also interesting is the Poake proposed project in New Zealand, which integrates a natural gas-fired supercritical CO2 power cycle known as the alum cycle, with an 8 rivers steam methane reformer unit to produce hydrogen. Whilst this isn't a coal-based demonstration, the earlier net power alum cycle demonstration in the USA shows that coal-based operation is feasible. In terms of costs, a number of analyses have been carried out to assess the costs of hydrogen production. In these studies, hydrogen costs vary significantly as a function of the production technology used, together with other local factors. This means that direct comparisons are difficult to make due to the varying assumptions. However, in general, blue hydrogen production routes are lower cost than green hydrogen based on water electrolysis, typically by a factor of around 3. Given the economic advantage of coal gasification and natural gas reforming with CCUS, it is likely that these will continue to be the lowest cost source of large-scale hydrogen in the near and medium term. Hydrogen produced by coal gasification and SMR of natural gas with CCUS vary from $1.4 per kilogram of hydrogen to around $2.4 per kilogram of hydrogen. As shown in this US DOE report analysis shown here, hydrogen from coal gasification with CCUS can cost as low as around $1.6 per kilogram of hydrogen. In terms of the breakdown of the cost of hydrogen production from coal, in the case of China, CapEx and OpEx requirements account for around 80 to 85% of the cost, with fuel accounting for the remaining 15 to 20%. The addition of the CCUS system contributes to around 5% increase in CapEx, with the largest cost addition being a 130% increase in OpEx. Analysis for the UK government by Element Energy points to there being a good technology development opportunity to reduce the CapEx as shown in the chart here, with perhaps a 45 to 50% reduction being possible by 2050. Further analysis by the Committee for Climate Change shows that future savings from economies of scale could reduce the cost of future coal gasification with CCUS by around 10 to 15% by 2050. This cost assumes 95% carbon capture rate and a carbon tax by 2050 of £227 per tonne of CO2, such that the carbon cost would account for 25% of the cost of hydrogen production. The potential for very high capture rates to approach 100%, as well as co-firing coal with a proportion of biomass or other waste carbon-based materials, is therefore a potential direction of development for coal-based CCUS plant. In regions of the world with access to relatively low-cost renewable electricity, green hydrogen produced using water electrolysis could in time become a competitor with blue hydrogen from coal or natural gas. The potential of cost reduction for water electrolysis is shown in the chart here, in comparison with hydrogen from fossil fuels with CCUS. It should be noted, however, that in this analysis by ARENA, the cost of hydrogen production from fossil fuels is assumed to be constant over the period through to 2050, resulting in an increase in the levelized cost of hydrogen due to the assumed increase in carbon tax over the period. As shown in my last slide, however, this is unlikely to be the case. But focusing on water electrolysis aspects of the study, the forecast is for hydrogen from low-cost wind to start to be competitive with the upper range of fossil fuel-based hydrogen prices in less than 5 years, perhaps competing with the lowest cost fossil fuel-based technologies by 2035. This again suggests an important role for low-carbon, fossil fuel-derived hydrogen into the medium term. Looking at the impact of the different hydrogen production methods, the chart here shows the estimated CO2 emissions per kilogram of hydrogen produced, where the CO2 impact of different hydrogen production technologies varies widely. The carbon intensity of hydrogen from unabated coal gasification is 19 kilograms of CO2 per kilogram of hydrogen, which is around double the value of the carbon intensity from steam methane reforming of natural gas. However, when CCUS is added, this carbon intensity can be reduced to below 3 kilograms of CO2 per kilogram of hydrogen as shown, based on 90% CO2 capture. In comparison, water electrolysis using renewable hydrogen only is close to zero CO2. But where grid electricity is used, which of course contains a portion of fossil fuel-based power generation, emissions can be around 25 kilograms of CO2 per kilogram of hydrogen, i.e. higher than unabated coal. The outcome of this is that in terms of moving towards net zero emissions, the impact of using water electrolysis could be detrimental unless the water electrolysis process is used at low capacity factor to use mainly renewable electricity. The number of countries producing hydrogen strategies and the scale of ambitions contained in them is increasing. To support these national strategies, the IEA has identified 5 policy actions through to 2030 which should be pursued to increase the uptake of hydrogen and the energy transition. In general, these policy signals are needed to provide key stakeholders with certainty that there will be a future marketplace for hydrogen. Climate policies in particular will be important, with potential actions including the establishment of high-level instruments such as emissions reductions targets or commitments to deploy certain energy resources or carbon pricing systems. A priority should be the deployment of hydrogen technologies at scale, where a good approach to achieve this would be to deploy clean hydrogen production at scale as part of industrial clusters. So finally, to conclude, the total global hydrogen demand in 2018 was around 115 megatons of hydrogen per year, which was produced local to the point of use, almost entirely from fossil fuels, with coal accounting for around 27% of the hydrogen supply. The global demand for hydrogen is forecast to increase, perhaps as high as 650 megatons of hydrogen per year by 2050. Hydrogen production from fossil fuels with CCUS are lower cost than green hydrogen based on water electrolysis, typically by a factor of around 3. Coal gasification with CCUS costs typically $1.6 to $2.4 per kilogram of hydrogen. Learning by doing through large-scale commercial rollout, together with cost reduction through technology innovations, could reduce the cost by perhaps 10 to 15% by 2050. In terms of emissions, the addition of CCUS can reduce the carbon intensity of this process to below 3 kilograms of CO2 per kilogram of hydrogen. Capture technology with increased capture rates approaching 100% should be explored in the medium to long term in the transition to 2050 to further reduce this, with co-firing being an additional option. Near-term actions are required to overcome the barriers and reduce costs to increase the uptake of hydrogen. This includes policy actions to send positive, long-term signals to potential investors. So overall, it seems clear that to produce low-carbon hydrogen at scale, fossil fuel sources, including coal, will continue to be needed in the medium to long term, particularly for industrial uses. Thank you for listening.